Brouwer's Fixed Point Theorem. Introduction. The theorem is a fundamental result in topology with significant implications for mathematical economics. It is particularly useful in proving the existence of equilibria in economic models. The theorem provides conditions under which a function must have at least one fixed point, a point that maps to itself. It has applications in general equilibrium theory, game theory, and other areas of economics. Statement of Brouwer's Fixed Point Theorem. Let X be a non-empty, compact and convex subset of a finite-dimensional Euclidean space, e.g. R to the power of n. If f is to X, right-pointing arrow X is a continuous function, then there exists at least one fixed point X element of X, such that f of X equals X indo. Key concepts explained. Non-empty. The set X must contain at least one element. Compact. In Euclidean spaces, compactness means the set is closed, contains all its limit points, and bounded, fits within some finite radius. Convex. For any 2 points in X, the line segment connecting them lies entirely within X. Continuous function. Small changes in the input of f lead to small changes in the output. Intuition behind the theorem. Imagine crumpling a piece of paper and placing it back within its original boundaries. At least one point on the paper must remain in its original position. The theorem generalizes this idea to higher dimensions and continuous mappings. Proof sketch. Intuitive. Consider a one-dimensional example with a continuous function f is to 0, 1 right-pointing arrow 0, 1. Plot f of x against x. The fixed point is where the graph of f of x intersects the line y equals x. The intermediate value theorem can be used to show that such an intersection must exist. In higher dimensions, the proof relies on advanced topological tools like the Borsuk-Ulam theorem or Sperner's lemma. Applications in economics. The theorem is a cornerstone in proving the existence of solutions in economic models. General equilibrium theory, specifically in the Arrow-Debreu model, used to prove the existence of a competitive equilibrium, a set of prices and allocations where supply equals demand in all markets. Setup. The set of possible prices is compact and convex, and the excess demand function is continuous. The fixed point is a price vector P, where excess demand is 0, i.e. Z of P equals 0, representing equilibrium. Nash equilibrium in game theory, used to prove the existence of a Nash equilibrium in finite games. Setup. The set of mixed strategies is compact and convex, and the best response correspondence is continuous. Fixed point. A strategy profile where each player's strategy is a best response to other strategies is a fixed point, representing the Nash equilibrium. Brouwer's theorem in dynamic systems ensures the existence of steady states or stationary equilibria in dynamic economic models. Example. In growth models, a fixed point represents a long-run equilibrium, where capital and output remain constant over time. Applied microeconomics. Matching problems. In two-sided matching markets, e.g., labor markets, school choice, the theorem ensures stable matchings exist. Auction theory. In auctions with continuous bid functions, the theorem guarantees the existence of equilibrium bidding strategies. Example. Existence of market equilibrium. Simple example of an exchange economy with two goods and two consumers. Setup. The set of possible price ratios lies on a simplex, compact, convex, and the excess demand function is continuous. Application of Brouwer's theorem. There exists a price vector where excess demand is 0, ensuring market clearing. Limitations and extensions. Continuity requirement. The theorem assumes continuity, which may not hold in some economic models, e.g., discontinuous utility functions. Convexity requirement. Non-convexities, e.g., increasing returns to scale, can violate the theorem's assumptions. Extensions. Kakutani's fixed point theorem generalizes Brouwer's theorem to correspondences, set-valued functions, useful for games with multiple best responses. Schroeder fixed point theorem extends the result to infinite dimensional spaces, useful in dynamic optimization problems. Conclusion: Brouwer's fixed point theorem is a powerful tool in mathematical economics for proving the existence of equilibria. It has intuitive appeal and guarantees stable solutions under certain conditions. Despite limitations, its extensions and applications make it indispensable in economic theory.